You got it? What is it?
Oh, we both was a question like about 36 and 38 of completion.
Mm-hmm.
We don't know which ones we didn't do because we did them all.
Same.
I think you thought there was some extra questions for a couple questions or something.
Ask me about it after class. I'll have to do something about it. I told the grader to give you guys a few so that I was trying to make the grading a little bit friendlier. I'm not sure he has actually implemented that on this one. But anyway, you can talk to me about that after class. Do you hit record? Okay, I'll start then. Dearly Father, we thank you for this morning. I thank you again for these students who just has to be with us today. Help us to understand just a little bit more about series and about how to understand their convergence or divergence. Lord, in your name I pray. Amen. So this topic is subtle, all right? So it's important you don't miss days of class here, especially, because if you miss a day, you might miss a lot. Now, so just to remind you, well, you guys know the definition, I hope. I should give you a little quiz on that a little bit later here. So, let's see here. Definition. Let Sn equal to the sum k equals 0 to n of a sub k. All right. Then we say the series. And what is the series? The series is a0 plus a1 plus a2 plus dot 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 dot, which we can more nicely indicate as the sum k equals 0 to infinity of a sub k. All right, this is the series. Does the following. 1, converges, right? If and only if the limit as n goes to infinity of s sub n, which, by the way, we could rewrite as the limit as n goes to infinity of the sum of k equals 0 to n of a sub k converges. And 2, it diverges. And this is in some sense, well, it diverges if and only if it doesn't converge, which we could also say as if and only if the limit, well, if Sn does not converge to L in the reals, okay? In other words, if the sequence of partial sums diverges. All right. In case one, the value limit as k goes to infinity, right? Rather, as n goes to infinity, of the sum k equals 0 to n of a sub k. This is, if that's a real number. In other words, if the series converges, this is called the sum of the series. All right. So this is what we mean by convergent versus divergent series. All right. What was the big example we did last time? I won't go back through the details entirely, but I'll just remind you, one of the examples we had was if we had the series a plus ar squared plus dot 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 dot. In other words, the sum k equals 0 to infinity of ar to the k, then we proved that that in fact converged to the sum a over 1 minus r, provided what? we needed some condition. What's that? R is not 1. Yeah, that's part of it. More specifically, what does R have to be? It could be negative even. Like R equals minus a half is fine. What's that? Less than 1. What is less than 1? Absolute value of R is less than 1, right? In other words, minus 1 less than R less than 1. In other words, R has to be an element of the open interval from minus 1 to 1. It's got to be that kind of number. This is called the ratio of the geometric series. This is a geometric series. I can give you, now that we've had a little time to let it sink in, here's a definition for you for a geometric series. Definition, if the series A0 plus A1 plus A2 plus dot 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 has A sub k plus 1 divided by A sub k equals to R, where R is a constant, all right? If that's true for all k, constant, right? Then A0 plus A1 plus dot 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 is a geometric series. With ratio R. So there's some terminology, just to have some standard terminology to refer to geometric series. Did I say Cheerios or Serios? I said something, it wasn't right. A geometric series is one for which if you take the ratio of subsequent terms in the series, right, you get a constant. Terms in a series. What's a term in the series? I just used a term we haven't defined. Any of these. For example, this is a term in the series. More generically, the A sub k, for any k, is a term in the series. I would say it's the kth term in the series, right? Although, in terms of counting, I could be off by 1 or more, right? I mean, the kth term in the series, actually, if you enumerate them, is the k plus 1th term if you go from, like A sub 0 is the first term, A sub 1 is the second term, if you're counting that way. So be aware of that issue. It's not a big issue, though. So far, so good? I want to show you guys another example. Well, yeah. So example, if we have the sum k equals 1 to infinity of, let's say, just a second, I got to do some math in my head, which is always dangerous. 1 over k times k plus 1. Is this a geometric series? Well, look at it. So let's just write out a few terms. This is 1 over what? 1 over 2? 1 times 2, right? Plus what? 1 over 2 times 3, right? 1 over 3 times 4 plus dot, 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 right? You can easily see that if you divide subsequent terms, you don't get the same. Right? If I look at a sub k plus 1 divided by a sub k, I certainly don't get a constant thing, right? This is clearly not geometric, right? It doesn't have the form a plus ar squared plus dot, 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 right? It's not geometric. It's something else. And this isn't especially enlightening either, right? Like it's a half plus a sixth plus a 12th, you know? So what can we do here? Well, you guys have studied something else before, right? You already know something called partial fractions, right? So maybe if we use partial fractions, we can understand this series better. Let's try that out. I mean, we've got nothing else to do at the moment, right? So let's do that. And you can do partial fractions, and what you'll get is 1 over k minus 1 over k plus 1. Now, if you don't believe me, you can make a common denominator on the right-hand side and see if I'm right, right? I get k plus 1 minus k. The k's cancel. I get back to here, yeah. So that's what partial fraction tells us, is that we can rewrite 1 over k times k plus 1 as that, right? So now I can calculate the nth partial sum. And instead of using this expression, I'll use this one, because it's nice. All right. And then we can just write it out, right? What do we have? We've got k equals 1. I've got 1 minus 1/2, right? Oops. Duh. This is k equals 1. And then plus what? 1/2 minus 1/3, right? Then plus what? Plus 1/3 minus 1/2, right? I'm an idiot. That should be a what? Fourth, right? So here's k equals to 2. Here's k equals to 3. I'll do all the way out to here. Let's see, I have like 1 over, let's say, n minus 2, minus 1 over n minus 2 plus 1, which is minus 1, plus 1 over n minus 1, minus 1 over n, and then finally plus 1 over n, minus 1 over n plus 1 when I get to the nth term, right? Here's k equals n minus 2, k equals n minus 1, k equals n. Now, I probably don't need to quite write as much as I did here. I'm doing so that you can really, really see what's going on, right? So if you've ever seen one of those like old-timey telescopes that, and I don't know, see, it's usually called the telescoping series, but how many telescopes do you know that collapse from both ends? Because that's more like what it is. I don't know, it's, right? It's the middle that's collapsing, the ends are staying, I don't know, however you want to look at it, but you can see things are canceling here, right? This, and that, and that, and that, right? Over here, this guy and that guy, this guy and that guy. And then the ones in the middle, of course, are canceling like something in here and something in there, right? I mean, there's something that I haven't written which it cancels with. And you can see that the only thing that remains from this entire thing is just the first term and the last term, right? Now, so we get what? 1 minus 1 over n plus 1, right? So again, a very precious thing and wonderful thing has happened. We've actually been able to straight up calculate the nth partial sum. I cannot emphasize to you how unusual this is to be able to do this. But we have, and so you can calculate its convergence really easy. What happens if n goes to infinity of this? Not 0. It depends on what you think I was pointing at, right? So you might have been right. The 1 over n plus 1 goes to 0, right? That goes to 1, right? So 1. Thus, the sum, k equals 1 to infinity, of 1 over k times k plus 1 is equal to 1. It converges. The sum of the series is 1. And this argument is pretty much just direct from the definition, right? It's kind of neat. If you look at what this is, what would this, I mean, just take a step to smell the roses here. This is a half plus a what? Plus a sixth plus a, what did I say, 12th? What's the next thing? 20th? What's the next thing? This is 4 times 5. 5 times 6 is 30th. What's the next thing? 6 times 7, 42, you know. It's weird. I'm not sure I would have guessed that unless I did a lot of numerical work. Right? But we didn't guess it. I mean, we just straight up showed that that is equal to 1 through a careful limiting argument, right? That's neat. Any questions about this yet? Okay. If you look at the video from yesterday, I think maybe towards the end, I forget, I worked one of these. No, where would it? It would have been towards the, somewhere in there in the middle. I worked a one with a telescoping series where it turns out that you get like 3 things from the start and 3 things from the end, which don't cancel. So you end up adding together 3 things to find the telescoping series. You can manufacture these things so that the cancellation only happens after you go out like 5 terms or something, and you'll keep the first 5, but then, and you'll keep the last 5. Usually the last 5 go to 0, usually. You could do stuff like, you know, this is another example you could do, which is kind of different. Something like this, inverse tangent of n minus the inverse tangent of n plus 1, you know. Oh, I said n. Well, you could use n. Fine, I won't. I'm trying to use k as the summation variable for a while here. So if you had something like this, right, what would happen is you'd get this, like, if you calculate the nth partial sum, stuff in the middle would cancel, right? And you'd be bookended with like a inverse tangent of 1 minus inverse tangent, and then like a minus inverse tangent of n plus 1 at the other end. As n goes to infinity, you'd get 1, I guess you get pi over 4 minus pi over 2 or something, right? So it doesn't always have to be that the thing over there doesn't matter. I mean, there are examples where it ends up contributing to the value. It just, with these kind of examples, it almost always goes to 0. All right, I digress. Enough about that. What is the connection between the, can you guys tell me, how do you connect the nth partial sum with the nth term? Or what's the connection there? Let me ask a reverse question. All right. Given Sn, all right, what is a sub k as function of the Sn? In other words, how can you relate the kth term to the partial sums? There's a very simple relation, actually. So what you do is you look at, let's look at Sn minus Sn plus 1, n minus 1 rather. I mean, as soon as I write that down, you're like, oh, of course, right? Because if you add the first n of them, right, and then if you add the first n minus 1 of them and you remove them, what you're left with is just the last one, right? So basically, this is, you take the difference between, you know, the first n terms in the series and then just the first n minus 1 terms in the series, and then what you're left with is just the nth term. I mean, we can be more specific. This is a sub n plus the sum, k equals 0 to n minus 1, right, by definition of the, nth partial sum, of the finite sum, rather, and then minus the sum, and you see what happens here. These guys cancel, right? And you're just left with a sub n. So if you want to get back, because you could imagine yourself given just the formula for the nth partial sum, and then an evil professor could ask you, okay, so then what's the kth term? You know? Well, the kth term is, so, for example, if I tell you that Sn is n squared plus 7, right? Then what? a sub k would be equal to s sub k minus s sub k minus 1, which would be what? Oh, cool. I did not expect that. So if the nth partial sum is n squared plus 7, right? That's the nth partial sum you obtain from summing odd integers. Like if I take 1 plus 3 plus 5 plus 7 plus all the way out to, 2k minus 1, well, 2n minus 1, let's say, then that's equal to n squared plus 7. This is a weird thing. I just made up n squared plus 7, guys. The fact that it worked out to an odd number is weird to me. I was not expecting this. That's cool. Does it work? I don't know. Let's try it for something like 11. What's 1 plus 3 plus 5 plus 7 plus 9 plus 11? Allegedly, that's equal to, so this puts k equals to what? 5. 6. Sorry, n, I should say n equals to what? Six, right? So allegedly it's what? 6 squared plus 7, which is what? 36. That's 43. Is that the case? Let's see, 20, 27, 32. What? 20, 27, 32. I can't do math. What did I do wrong here? 20, 27, 32, 35. I get 36. I have what? Yeah. Is my starting point right? If I put in k equals 0, what do I get there? Oh, I see the problem. Where does it start? K equals 0, where does it start? All right, so I have to, right. In other words, this n isn't right. N should be 5. So 25 plus 7, 32. And you can see that's what we have, 20, 27, 32. Did I do something wrong still? I'm going to erase this for a second and just start over because I've got something wrong and I don't know what it is and it's not. So let's see here, let's try this again. So I'm looking at, let's just do the sum. Let's start k equal 1 to n, right, of 2k minus 1. it should still allegedly be n squared plus 7. Okay, yeah. Let me try that. Let me try this out. So if I have, for example, n equals to, well, we were trying what, 6? Right? We were trying 6. So that would give me 1 plus 3 plus 5 plus 7 plus 9 plus 11. That's this guy. Is that in fact equal to 6 squared plus 7? I think I've still got my counting off. 27, 32, 35, 36. I'm still off. I guess I have to start at 0. I'm sorry, guys. I don't know. What have I done? They'll teach me to try to check my work. Something stupid. I'm off by 1, right? I mean, this relation, right? Look at this derivation up here. It doesn't matter whether you start at k equals to 0 or k equals to 7. This should still be a relation, which is true, right? Because the starting point for the series doesn't, starting point for the finite sum it cancels out whatever it is, right? This should be true, independent whether I start at 0 or 1. So if I say that the nth partial sum is n squared plus 7, you could do that. Then I should be able to calculate a sub k, s sub k minus s sub k minus 1, right? Huh. Well, I'm going to leave this for now. I'm going to put a question mark here. If you can explain this to me before tomorrow, you can earn 5 bonus points. So there you go. Let me make it into something that you can do something with. There you go. Let us go on. So our next theorem is as follows. If you have the sum over a sub k and the sum over b sub k converge, let's say with sums, let's say a and b respective, all right? And if c is a real number, then the sum over a sub k plus b sub k is equal to a plus b. All right. In other words, it's the sum over a sub k plus the sum over b sub k, right? And if we have c times the sum over a sub k, well, that's equal to ca. In other words, sorry. In other words, you can pull the constant out of the sum, provided, of course, that it's a convergent sum. And if it's divergent, if you have a divergent sum and you multiply by a constant, it's still divergent. That's also true. But I'm going to focus on the convergent case here for now. All right, so this is very bothersome to me. I must let it go, though. We have other things to do today. All right, so here's the proof. What does it mean for the sum of a sub k or b sub k to converge? So we have what? We have S, so assume, sum AK and the sum BK converge, right? Now, when you do that, this notation, what it's saying is you could start the series wherever you want, all right? Now, just to give you a concrete proof, I'm going to suppose that we're starting from k equals to, let's say, 0. But the point is of saying the theorem as we do is that you could just as well start anywhere else. All right, I'm going to give you a proof that starts at 0. And I think it's fairly obvious how to make it start somewhere else once I show you this one. Okay, what's that mean, these converge? With sums. We have what? We have, first of all, the nth partial sum for A. I'll put an upper A. Sum k equals 0 to n of A sub k, right? This sequence goes to A. And what else do we have? The nth partial sum for B, which I'll write as the sum. I'm just defining these symbols at the moment. K equals 0 to n of B sub k. Well, that converges to B, right? These two facts are given to us. That's what it means to say that the series with terms A sub k and the series with terms B sub k converge to A and B, respectively, right? So what does it take to prove that this thing, the series with terms A sub k plus B sub k converges? Well, consider if we say Sn, right, the nth partial sum of the sum k equals 0 to n of A sub k plus B sub k, right? What's this equal to? Properties of finite sums, right? The sum of a sum is the sum of the sums. Sorry. In other words, I can break up the sum like this, right? That's just, what is this by properties of finite sums, right? But this is what? This is equal to, that's nothing more than S, the nth sum for A, and that's the nth partial sum for B. And goodness gracious, let's be a little bit greedier. Check this out. What if I squeeze a little c right here? Then where else would it go? I could pull it out here, like so, right? It multiplies here. And then what does this final expression tend to as n goes to infinity? The limit as n goes to infinity of S sub n is equal to c times the limit as n goes to infinity of Sn upper A, right? Plus the limit as n goes to infinity of Sn upper B, but by definition, this is what? A and B, those are the sum of the series A sub k and B sub k respectively. In other words, the limit of S sub n as n goes to infinity is c times A plus B. Now this proves the theorem because if you take, we can look at some special cases and get everything we want, right? What happens if we set B equals to 1? set c equal to 1 rather. C equals to 1 gives us what? This gives us the sum of a sub k plus b sub k is equal to the sum of a sub k plus the sum of b sub k, right? And how do you get the other result? Can you see it? I mean, we've just shown this is true for arbitrary a, b, and c. What do you want to make b sub k equal to in order to see the other result that I've claimed? This one right here. Just assume you're working with the 0 series for b, right? Just set b sub k equals to 0. That gives you the other case. So. All right. All right, let me get that out of the way. So, I mean, this is the first and most basic of series tools we have to work with, right? The sum of convergent series is once more convergent. The scalar multiple of a convergent series is once more convergent. That's very nice, right? Because you could have, like, I mean, here's a standard kind of example built over this theorem, something like this, right? Suppose you had the sum k equals 0 to infinity of something like, I don't know, 1 over 2 to the k plus 1 over 3 to the k. This is not geometric, but it is the sum of geometric series. See, what this is it's the sum over 1 over 2 to the k plus the sum 1 over 3 to the k. Now, the reason I can make the step I just made is I took a logical loan on the assumption that these things I'm writing actually do exist. Now, let me just expand on that. This is, so that's like 1 plus a half plus a fourth plus da-da-da-da, right? And this over here would be 1 plus a third plus a ninth plus a, so forth and so on. So here we have a equals to 1, r is equal to a half. Here we have a is equal to 1, r is equal to a third. So what we have then is we've got 1 over 1 minus a half plus 1 over 1 minus a third. Now, that's interesting because, let's see, how's that? That's what? So we have 1 over 2/3, right? Plus, I'm an idiot. What's 1 minus a half? 1/2, right? 1 minus 1/3 is 2/3, okay. So the answer is 2 plus 3/2, aka 5/2. No, wait a minute. 7/2, right? So this theorem might not seem like much to you, but you should realize it actually opens the door for a whole new host of examples. It's a very useful theorem. It allows us to divide and conquer, right? If a series is built from adding together other series we already understand how to analyze, then we can rip it apart to pieces, into pieces, and analyze those sub-series one at a time. Any questions? You guys are awful quiet. Making me nervous here. This theorem is the most abused and misused theorem that I will tell you. It's amazing it keeps coming back to allow itself to be studied. If I took this much abuse, I probably would give up on math. Let's see here, kth term test. All right. And actually, this isn't, well, I call both of the following things I'm about to show you kth term tests, but here's one side of it. The kth term in a convergent series tends to 0. Let me state that a little bit more explicitly. Now, I mean, I think the text has used words, so I'm using them too, but I think some less words is good here. If the sum, this is more precise, if the sum k equals 0 to infinity of a sub k converges, all right, then a sub k goes to 0 as k goes to infinity. We have seen some counterexamples to this. In our previous lecture, I had a couple series where we had terms which don't go to 0 as k goes to infinity, and we got infinity. Like we added the number 1 together over and over and over and over again, and that diverged, right? Here's the proof. What is the proof of this? Well, observe a sub k is equal to Sn minus Sn minus 1. I know you're a little worried about, you might be, if you're like me, you're a little bit worried about what it is I'm missing over here at the moment. Because it's kind of important to this proof. And then what? Well, sorry, this should be what? K, yeah, k and k minus 1 in my current formulation. If you take the limit as k goes to infinity of a sub k, what do you get? The limit as k goes to infinity of s sub k, which exists, so I can do this, right? So limit laws apply here because the convergence of the kth partial sum is given to us. We usually say nth partial sum, but you could say kth partial sum. Of course, these both exist, right? Now, if you take k going to infinity, it's the same as k minus 1 going to infinity, right? You understand both of these limits must go to the same thing because, I mean, if I have the inverse tangent as n goes to infinity goes to pi over 2, what's the inverse tangent of n plus 3 or n minus 3 as n goes to infinity? It's the same thing, right? Either way, you're taking this thing to a very, very large, input. So this is equal to 0. These have to cancel. They both exist and they're both equal to the same thing. And there you have it. Almost more important than this is the corollary to this, which he doesn't call corollary, but I'll call corollary. 12.26, right? If a sub k does not go to 0, then the sum k equals 0 to infinity of a sub k diverges. So what are some, I mean, this corollary is really, really nice because it's so simple. Like, for an example, if I have the sum, say k equals, 1 to infinity of something like k squared over k squared minus 42. Well, I have k squared over k squared minus 42. That's my a sub k, right? That goes to 1, which is not equal to 0. So therefore, this series diverges. by the kth term test. Man, that's a lot less work than we've done for other things, right? So in the study of given a series, does it converge or diverge? If you can look at the kth term and see that it goes to something other than 0, game over, end of story, that series diverges. That is nice and cut and dried and simple, right? If I put one of those on the next test, I hope you all get it. I usually put 1. Here's another example. If I take the sum, k equals, say, 0 to infinity, of the inverse tangent of k, this diverges. Since inverse tangent of k goes to pi over 2, which of course is not equal to 0 as k goes to infinity. Yeah. And I should say diverges by kth term test. Okay. Now, I could also do something like the sum of cosine or the sum of sine. Those have limits which don't exist, right? Limits which don't exist are also not equal to 0. Those would be another example you could give. Do you guys have any questions? Okay. What's the temptation here? And this is the abuse I was talking about, you guys. The thing people tend to say, which is not true, which I will never say. If I ever say it, you have to fire me right there and then. I have to find a new job. Like it's such a hideous thing and wrong thing to say. It should never be said. I hate to even say it to give you an example of what's wrong, but I feel obligated to mention it since it's such a popular wrong belief. And it's this. If the limit as k goes to infinity of a sub k equals to 0, right? Then the sum k equals 0 to infinity of a sub k converges. This is just simply false. Let me put a big, let me fix this before I, incorrect. This is not how it works. There's a very big difference between that statement and that one, right? If it doesn't go to 0, then it diverges. That does not automatically then mean that if it goes to 0, it must converge. It's not logically follow. Now, so here is an example. Let me give you an example. Here's an example which alone, this one example is enough, should be enough to convince you that you can't do it, right? If we study the sum, k equals 1 to infinity of 1 over the square root of k. Okay? And I think I got this example from your text, but it's a great example, so I'm going to give it to you. It's pretty easy to understand. If you calculate the nth partial sum for this one, right? What is it? It's 1 over the square root of 1, 1 over the square root of 2, 1 over the square root of 3, plus plus 1 over the square root of n. First of all, observe that a sub k is 1 over the square root of k, right? And that does go to 0 as k goes to infinity, right? So if this thing I just told you is wrong, if it was actually right, then this should converge, right? I'm about to show you that it most certainly does not converge. Let me show you how. So we play the game we usually play. How do you make... Now I want to show that this diverges, right? So I really want to find something smaller than it that also blows up, right? So this is greater than or equal to what? How can you make each one of these fractions bigger in a nice kind of unified way? Well, how about this? What's the smallest thing here? It's this guy, right? So like 1 over the square root of n is smaller than, so I could just change them all to 1 over square root of n, right? You guys agree? I mean, you should agree. I've made every single summand here either the same or smaller. How many of these are there? N-fold sum. It's an n-fold sum, right? There's n things being added together there because I started at 1. So you can rewrite this as what? N over the square root of n, but we know algebra, so we know that this is the square root of n. And that, quite clearly, does not converge. If the nth partial sum does not converge, that means the series does not converge. The series diverges to infinity. And yet, it has the kth term going to 0. Game over, right? You can't do that. This example alone is enough to show you the error of your ways there, I hope. It is nevertheless, I often refer to this as the wishful thinking test. As in, I wish it was that simple, but it's not. Okay, so it's subtle. It's subtle. What I'm trying to say is, if the nth, so like, we're kind of, as we go on here, we're building some kind of big flow chart, right? So you've got a series. You're given, a sub 0 plus a1 plus da 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 da, and you start, right? Your first thing you do is, does a sub k go to 0, right? If the answer is no, it's like game over, diverges, all right? If the answer is yes, then that takes us to other tests, all right? There's like 6 or 7 of them that we're going to learn. But this is the gateway test. Does the kth term go to 0? If it doesn't, it's easier. Okay. Questions? No, I'm going to go on. No. All right. So the next term is, sorry, where was I? The next, we're in section 12.3. The next thing is a series with non-negative terms converges if the sequence of partial sums is bounded. So in section 12.3, we study a particularly nice kind of series. And that kind of series is a series with non-negative terms. So we're studying the sum k equals 0 to infinity of a sub k, where a sub k is greater than or equal to 0. So what can we say about such a series? Notice that the nth partial sum, right? If we look at the nth partial sum, it's equal to what? It's equal to a sub n plus the sum k equals 0 to n minus 1, right, of a sub k. Which is what? This is equal to a sub n plus s sub what? N minus 1. But if a sub n is greater than or equal to 0, this shows what? S sub n is greater than or equal to s sub n minus 1. Therefore, s sub n is an increasing sequence, right? There's supposed to be a G in that. Increasing. No, okay. I should just should go back to my roots. There we go. Can't mess that up. So if we've got an increasing sequence which is bounded above, what do we get to say about it? Bounded monotonic sequence theorem, right? It converges to its what? Its least upper bound. That's the first theorem. A series with non-negative terms let's say whose sequence, let me just use the language, whose Sn is bounded above converges. Proof, again, is just by the bounded monotonic sequence theorem and the fact that we just showed that such a sequence is increasing, right? The sequence of partial sums is increasing. If it's bounded above, it converges. So that's that theorem. I don't really have an example for that at the moment, but I think we really end up using it in the proof of the integral test. But I don't have time to do the proof of the integral test today, so I think I'm going to go ahead and go on and talk to you about the basic comparison test instead, and the limit comparison. We'll come back to integral test tomorrow, probably. So what's the comparison test? Basic comparison. This is called basic comparison versus limit comparison. Basic comparison test says that if a sub k is less than b sub k, right, and I think we also have 0 less than or equal to a sub k, less than or equal to b sub k. So we're looking at series with non-negative terms, all right? And if this is true for k sufficiently large, in other words, there exists some positive integer. If there exists some positive integer for which this inequality is true, for everything beyond there, right? That's all we need. If that's the truth, if that's the case, then we have a couple things. Number one, I'll start us out here. If the sum over b sub k converges, then the sum over a sub k, the series formed from adding a sub k together, converges. Also, the sum of a sub k is actually less than or equal to the sum of b sub k. And if here, of course, I'm referring to the sum when I write the inequality. But what's 2? Right. If the sum over a sub k diverges, then the sum over b sub k diverges. Notice the juxtaposition in the role in the inequality, right?